In this video, we'll start talking about the maintenance of equipment, that is your routine equipment use. One of the key factors that you need to understand when you're talking about routine equipment use is equipment calibrations. So in this video, we will look at equipment calibrations. All equipment in a laboratory, new and existing, need to be calibrated, maintained and validated on a regular basis to ensure accurate and reliable functioning. Let's examine the details of calibration. Equipment calibration can be defined as a process of verification by comparing the accuracy of a measuring or a test instrument against a reference standard. Would like to mention here that calibrations are required both for equipment and for your analytes that you are using in the equipment. So how does that work? Equipments need some kind of a coarse tuning. If you remember, there's a coarse tuning, which is your adjustment of your equipment, and some fine tuning are done for the analytes using some material called calibrators. Both these concepts are important, though in this video we'll only talk about the equipment calibrations. When you're looking at this picture, let's assume that the reference standard is a white dialed watch. So comparing to the white dialed watch, you see that the black dialed watch is about 4 minutes slower. Therefore, you look at one equipment which we have to consider as a standard and adjust the other equipment against that standard. Such a process is known as calibration. I hope that is clear. It is putting it too simplistically. You are looking at one equipment which is considered as a standard and you are adjusting the other using the reference. So calibration needs to be performed for both analytes. In this section, we are only talking about equipment calibration. I said that a minute ago. You need to know that your standard is correct. It's an important thing. You just decided in the earlier slide that the white dialed watch is correct. In the above example, we just decided like that. But how do you know that? How do you know how correct that is and what errors that could be having? Such concepts are included in the calibration process. Thus, the comparison of accuracy should be defined within limits of uncertainties. We will talk about these concepts in detail in the later parts of this video. Thus, the aim of any calibration process is to detect, correlate, and if possible, eliminate by adjustment any discrepancy in the accuracy of the test equipment being calibrated. I hope that is clear. As components age and equipment undergoes changes due to variation in the environmental temperature and humidity or sustains mechanical stress, the performance gradually degrades. This is called a drift. When this happens, test results become unreliable and the quality of the results suffer. Any parameter of an instrument that will affect the quality of the test result has to be calibrated. Example, in the case of a refrigerated centrifuge, the parameters to be verified are speed, time, and temperature. I hope you have understood that concept. Any parameter, any aspect of an instrument which will affect the quality will require periodic verification for accuracy. This process is called calibration. Certain basic elements to be addressed as part of calibration are, first one is the calibration interval. How often do you calibrate? The period of time between successive scheduled calibrations. This depends upon the usage rates, conditions of use, skill level of the personnel using the equipment, degree of accuracy expected as per your laboratory requirements, and the manufacturer's recommendations. You can get some idea of what the frequencies of calibration are if you refer to NABL 112. It's a free download document. It's a document of NABL, which is an accrediting agency for laboratories, and have specified certain durations when calibrations are warranted. But then the final decision, if you want to calibrate more often, is yours. If you feel that your equipment is being used excessively and requires verification on a more frequent basis, it's entirely up to you to do that. And now we come to two important concepts with regard to calibration. We have already mentioned these briefly in the early conversation, and these are measurement traceability and measurement uncertainty. These are new concepts, and we will explain this to you further in the next slides. First, we will take up measurement or meteorological traceability. This is the most important concept in calibration. Calibration must be designed and operated to ensure that measurements made by the laboratory are directly traceable to national and international standards of measurement through an unbroken chain of accredited calibrating laboratories. That sounds like a lot of information, so we'll break it down for you and see in the next slides how and why we have to do this. Very important to establish traceability to an international system of unit or the SI unit for calibrations. When a valid traceability chain to the SI unit is established, it ensures that the working device is properly calibrated and, if correctly used, will produce valid results. Look at this pyramid here. At the top, you can see what is said as an SI unit, which is a legal unit. I will come back to this in a minute. The second and the third layers you see are primary standards, secondary standards. Moving further down, you see reference standards. Further down, you see working standards. And finally, you see at the base of the pyramid, the test and the measuring instruments. The legal unit or the SI unit, which is the most accurate measure for volume, weight, length, temperature, or whatever you are measuring. That is the final accurate unit. That is the ultimate absolute unit of measurement in the case of whatever is being measured. However, it is not possible for all laboratories in the world to compare their measurement with the legal units, is it? It's practically impossible that every lab can measure their accuracy against the ultimate legal unit or the SI unit as shown at the top of the pyramid. And so there are primary and secondary standards which are made by comparing with the SI units, and these are available in every country with certain organizations. In India, the reference material custodian is the NPL or the National Physical Laboratory. So now you see that an unbroken chain between the SI unit and the primary and secondary standard is being established. But then again, in a country like India, there will be so many laboratories. So is it possible for everybody to compare with the primary or the secondary standards? Possibly not. So there are further links in the chain which are made as reference standards, working standards, etc. You will see this one when you look at the picture. Therefore, it is important that an unbroken chain of comparisons is developed as far as practical, keeping in mind the degree of uncertainty of measurement that increases as the chain goes down. The degree of uncertainty must be mentioned on any calibrator or calibration certificate depending on which the laboratory can decide the acceptability. This unbroken chain of comparisons is called the traceability. I hope that concept is clear. Going back to the picture, you see that the chain of comparisons starting from the SI primary standards, going to the secondary standards, through reference standards and working standards to the measuring instruments. If you look at the right side, you see this arrow going up, which is the traceability of the material or mechanism that you are using for your comparison. And if you look at the arrow that's coming down here, that is the dissemination of the standard. So the traceability goes upwards, dissemination comes downwards. If you look at the left side, there's another arrow coming down, and that is your degree of uncertainty. And you can see that as the dissemination of the standard comes down, the degree of uncertainty increases. If the uncertainty is very small at the initial phase, the uncertainty increases to a much more substantial amount of degree as it reaches the testing or the measuring instruments. However, there are limits to the degree of uncertainty which is acceptable, and that's what I said about the uncertainty must be mentioned on any calibrator, and you can decide if this calibrator is okay for your laboratory. In India, the traceability of NPL and is evidenced by the certificate of accreditation to ISO 17025, and we'll talk about this again in later sections. The reference material you use in your lab or those with which your external agencies calibrate your equipment need to demonstrate this kind of traceability to ISO 17025. That is generally given in your calibration certificate. We'll show you an example later. To reiterate, as you see here, there is a dissemination of material in a traceable way, but with a certain level of increasing uncertainty. That was just a reiteration of what I said earlier. I hope that concept is fairly clear to you. Once again, since a new concept, I would like to reiterate with another illustration. Traceability is an unbroken chain of comparisons. Look at the links in this chain, in which every instrument in the chain is calibrated against a more accurate instrument immediately above it in the chain. Remember the picture from before? Calibration thus is the linking of measurement standards and or measuring instruments to relevant national or international standards through an unbroken chain of comparisons. Again, to reiterate, national traceability is to the National Meteorology Institute or Laboratory, NPL, New Delhi, and the international to the SI system of units in BIPM, France. After traceability, the second concept that requires mention in the case of calibration is the uncertainty of measurement, something that we need to understand in detail. Every measurement is subject to some uncertainty, even the SI units. A certain amount of variability is observed in repeat measurements results even if the measurement system is perfect. This is an inherent characteristic of a repeat measurement, and this can be due to the measuring system, analyte being measured, the environmental factors, the operator variance, or other sources. A measurement result is only complete when a